Hello everyone, welcome to this tutorial. My name is Emerson Ahrari. I'm a Google Earth Engine specialist. In this tutorial, I'm going to show you how to extract the environmental trends without seasonal impact using decomposition process in Google Earth Engine platform Python API programming. This tutorial is useful for those of you who are working on environmental monitoring. This tutorial can be extendable to all of the environmental variable available with multi-temporal frequency. So, let's begin this tutorial and make a new notebook in the Colab environment, just like this. And then start with importing essential libraries related to the Google Earth Engine platform. So, start with Earth Engine, then GEE map. Another new library is the XEE. It's a revolutionized library developed by the Google community, allowing us to combine Earth Engine and X-array data structure that extend our capabilities for satellite data analysis. So it is not available in the Google Earth in the Colab environment, so we need to install like this. Install XEE and then import. So another variable, another complementary library is X-array as XR. Remember to import the matplotlib, the essential library for, import matplotlib.pyplot as PLT. That is essential for plotting process. Let's run the first cell, and now Colab is connecting with the server and then the library is importing. If you're faced with any challenge in this tutorial, the code example attached below this video in the description box on my YouTube channel. You can compare my code with yours, and if problems still exist, feel free to reach me out on my channel. So let's clear the output and establish a connection between Earth Engine and Colab environment using EE library. Start with authentication first, authenticate, and then initialize. Project name. So you need to enter the Google Cloud project name associated with your Earth Engine account. To find it, go to the code editor environment first, and then upper right you will see your account information. Go to project info, and here it is, the cloud project name. Just copy and paste it into your code. For mine is this, but you need to add yours. Another one is another argument, OPTURL. Back to the X-array page. If you search on the net about XEE and Google Earth Engine, you will find a GitHub page including a detailed instruction about how to use this library regarding to Earth Engine analysis. OPTURL address available here. Paste it into your code. Let's run the code. Colab asking permission to establish a connection between Earth Engine and Colab through the associated accounts. So click on OK and continue. After a few moments, the connection established, and now we can use the Earth Engine capabilities in the Colab environment under Python scripts. So we need to identify the region of the interest, create a new variable from GEE map called the map function based on a base map like satellite view. Print the map. After a few moments, there is a user interface allowing you to select and draw your region of interest through the drawing tools available here. I'm gonna select an agricultural area on my own country, Iran. In the southwest of Iran, near to Persian Gulf, here you can see agricultural areas available here. I'm gonna monitor the water deficiency in this area using TerraClimate product. So, to select this region, you can use the, for example, rectangle tools available here, just like this. So, in the next step, I'm gonna have the rectangle as a variable. So, ROI sets to from the map, select the last feature that is drawn, then convert it into a geometry format. Let's print the ROI, and then you will have a polygon with coordinates explaining the region of interest. In the next step, I need to call the satellite data. Go to the code editor environment, through the search places and dataset, find TerraClimate monthly product available here. So let's import it, and here it is available through a link. This is easier to get access to the data and find its description. If you go to the bands, here you can see the spatial resolution is 5 km and dataset available since 1958 with monthly frequency offering several water-related parameters. One of the most important one is the climate water deficiency with a corresponding scale factor that we need to apply on the water deficiency parameter. So let's make a variable for TerraClimate or water deficiency. So collection, the variable name, make a tuple, and then copy the image collection or Earth Engine snippet, just like this. So in the next step, define a filter date ranging your data through a long period of time. For example, since 2000 to 2025 or even longer. So longer period helping us to get a better understanding about how environment changed during the time. For example, from 1980 to 2025, we need to understand about deficiency in this area. The target band is the deficiency. So then we need to apply the scale factor 0.1 on each data available through the time. Here, make a loop structure and then a function like lambda. So IMG, each input image considered as an IMG, and each IMG multiply to the scale factor. The output will have the properties of the input. img.property names, just like that. Let's run. And after a few moments, print the collection, and here you can see over 500 elements available through the times. In each date, you can see the deficiency or the water deficiency estimated or extracted, and also the scale factor applied on each existing data here. So in the next step, we want to use the XEE capability to transform an image collection format into a multidimensional format or X-array structure. So a dataset sets to from XR library called open dataset. Input data will be collection based on EE protocol. We want to do conversion. The output coordinate system EPSG 4326 describing WGS84, and this is a unique ID explaining WGS84 for all around the world, no matter where you are working on. So, and region of interest already settled through the ROI, and the scale express the spatial resolution or the pixel size. Actually, the pixel size is correct, not the spatial resolution. The scale value here, or the pixel size, is based on a degree because we are using WGS84. For example, a scale number 1 shows 100 kilometer, 0.1 shows 10 kilometer per pixel, and 0.01 means, for example, 1 kilometer. So 0.05 is 5 kilometer. Actually, it is the closest value to the spatial resolution offered by this satellite product. And the important thing is that the terraclimate is not a direct satellite estimation. This is a combination of satellite data, models, and gauge data. Actually, this is an assimilated product. So, let's run the dataset. After a few moments or a few seconds, the new dataset created. You can see from a image collection format, the data transformed into a multi-dimensional structure. We have a deficiency variable including 3 dimensions like time, longitude, and latitude. And here you can have a preview about the lat, lon, and time. So in the next step, this is an array structure. So when you convert the data into an array structure, it is easier to analysis and process. And then we can actually extend our capabilities and resources regarding satellite data analysis, because there are various libraries in all around the world can be useful for the array analysis. So now in the next step, I need to actually calculate the average deficiency for this region, because you can see the area extended over 3 longitude and 3 latitude, but we need one single value through the time, because here the spatial resolution or spatial information doesn't matter. Only we need to see the water deficiency dynamics through the time. So the DS average, we need to calculate the deficiency over the region. DS mean sets to get the DS, calculate the average over longitude and latitude dimensions. Let's run again. After a few seconds, the average calculated. So just like this. And now you can see the latitude and longitude no longer exist. Only we have time and a variable, the value of the water deficiency through the time. So now let's convert it into a data frame. In the data frame format, it is easier to analysis, specifically in the next step. Dot to data frame converted the data into the data frame structure. So, but we need to assign it into a variable like the df. So just like this. We have a data frame including 2 columns. The first time and the second is the deficiency. Even we can actually make a plot to get a better understanding about what's going on in this area. As you can see, it is very hard to understand what's going on because we have actually the seasonal impact on the data, and it is really hard to figure it out trend, if there is any trend, or it is increasing or decreasing. So in order to get a better understanding about the trend and monitoring in this area, I suggest you to use the seasonal decomposition process that its library is available on Colab environment and helping us to get a better insight about the satellite data dynamics through the time. So now let me to call a new library from statsmodels.tsa.seasonal import seasonal decompose, just like this. So make a model for a decomposition, call seasonal decompose, just like this, and then enter the rest of the uh, necessary arguments. The first one is the data frame dot def. Let me check it. That what yes, def is the name of the variable, but it is better to write like this. The model should be additive, and the next parameter argument is the period. The data is monthly, means we have 12 image or 12 data per year. So that's why the period should be 12, just like that. Let's run, and model is ready. Model.plot. We want to see the model output or model actually results from plt.plot. So let's run to see the output information. So as you can see here, we have a couple of plots here. The first is the normal observation, what we had before. So, and the trend is actually the variations or the dynamic values subtracted from seasonal variation. The trend is the observation in which the seasonal is subtracted. So now it is easier for us to understand about the about the trend dynamic in this area. Clearly obvious that the trend is increasing in this area, meaning that the water deficiency increasing in this region. So now I want to have the trend as a separate variable. So now here it is, a new variable df trend sets to from the model get the trend value df trend. Now you can see we have the df trend value. Some of the values are none. That makes sense. That's because of the type of analysis. And now we need to apply the Mann-Kendall trend analysis to get a better, to get more information about the trend characteristic. For example, it is true that we can see the trend is increasing, but statistically we need to confirm the increasing is significant. So, or it is important to know since when the increasing process started. Let's make a plot first to make sure that everything is fine, even we have some non-values in the start and in the beginning and end of the dates. So in the next step, let's call the Mann-Kendall library in the Python. So pip install Mann-Kendall and import it Mann-Kendall as mk. Another library is homogeneity, allowing us to understand since when the trend started, if it is significant. Pip install homogeneity. Import it as hg. Let's run. You can see the Mann-Kendall successfully installed and homogeneity 2. So in the next step, we can easily apply or calculate Mann-Kendall and Petit test based on the trend extracted trend or unextracted trend. So Mann-Kendall test, MK test, a new variable from MK call the original test, df trend. So HG test from homogeneity call Petit test, df trend again. Print the results. First, print the Mann-Kendall MK test, print HG test, Let's run. You can see the computation is running. Something is wrong here. So HG test. Yes, there is a typo here. Calculation running. So as you can see, the MK test, Mann-Kendall test, the trend is increasing. It's confirmed that the trend is increasing, and as you can see here, the p-value or that shows the significance is around 0. That is less than 0.5%. That is really good. And the slope of the variation is positive, meaning there is an increasing value. What about the Petit test? The Petit test also confirming the increasing trend that is started since 1999. So as you can see here, the change point started since the 1999 August. It was the main date in which the increasing trend started. And here, as you can see, the average deficiency was 159, but after the change point, the average deficiency increased to 170. So that was a comprehensive information about the trend detection and change point monitoring through the satellite data. Remember that this tutorial and this technique applicable to all kind of satellite data available with multi-temporal frequency, and this is not limited to only the deficiency. You can use it for all other factors and parameters available through the time, and and also the methodology also you can apply it for all around the world, not only limited to one location. I hope you liked this tutorial. If you had any question or any problem regarding this tutorial, feel free to reach me out on my YouTube channel, and then we can actually help you to figure it out about the problems you are dealing with. Thank you for your attention.